I am Larry Hatcher. This is Psych 302, Computer Applications in Data Analysis. And we're going to go through lecture notes for chapter 050, T-Test for Independent Samples. Reminder to my students, Psych 302 students, you do not need to download the data set or perform the analyses described in these notes. You should simply use these lecture notes as a guide when you complete your exercise, which will involve a different data set and, in fact, a different video. Let's scroll down to page 2 to get introduced to the statistical procedure. Independent samples, t-test, basic concepts. T-test for independent samples is sometimes called students' t-test for independent groups. It's used to determine whether there's a significant and substantial difference between the means of two samples. Specifically, the analysis is performed on a single continuous quantitative criterion variable. It involves a single predictor variable, and this predictor must be dichotomous, that is, one that consists of exactly two groups, just two samples, just two conditions, just two levels. The procedure used to analyze data from a between subjects research design. A study with one sample of participants in one condition and a totally unrelated sample of participants in the second condition. Our fictitious study, the employment and health study. Imagine you're conducting a program of research on attitudes and behaviors related to eating, exercising, and health. As part of your program of research, you've developed an instrument called the Questionnaire on Eating and Exercising, which was used to obtain the variables to be analyzed in this chapter. You administered your questionnaire to 260 students enrolled in a variety of psych courses at a regional state university. You obtained usable responses from 238 participants. Let's scroll down. I'm on page 4, at the top of page 4. Starting jamovi and opening the data set. Need help getting started? See lecture notes, chapter 025. Since it's likely this is going to be one of your first experiences with jamovi, the first few pages of this handout will give you some tips on getting started. If you need more detailed guidance, see my handout titled Lecture Notes, Chapter 025, Descriptive Statistics. In particular, see the part titled Downloading the jamovi data set from Canvas. Scroll a bit further down on this page, starting the jamovi application. If you're using a Windows computer and jamovi is already installed on it, you'll start jamovi the same way you start any application. Just click the Start icon in the lower left corner of the screen, scroll down to the J section of the resulting list of programs, open the jamovi folder, and click jamovi. If you're instead using the cloud-based version of jamovi, click the following link or just paste it into the address box of your browser. Clicking the above link may produce a dialog box asking whether you wish to continue as a guest or signed in using Google, Microsoft, or jamovi account. Make your selection and the jamovi interface will appear. It'll look something like this. Here's our initial jamovi interface. Finding and opening your jamovi data file. I am on page 5 now, halfway down page 5. Now that jamovi is open, you'll use the jamovi file panel to locate your data file and open it into the jamovi spreadsheet. When ready to perform the steps described in the callouts that I've added to the screen captures below. When ready, perform the steps described in the callouts that I've added to the screen captures below. Although the following instructions assume you're using the version of jamovi that's been installed in your computer, steps are very similar if you're instead using the cloud-based version. Here we have the jamovi interface. We begin by, at the top left of the jamovi interface, select the file icon, the air vent icon. You'll remember that's the icon that is 3 horizontal lines. In the resulting file panel, and this is the file panel, in the resulting file panel, select Open. In the resulting Open panel, select Browse. In the resulting Open dialog box, navigate your way to the drive where you had saved the jamovi data file. Double-click the name of that data file, and in this case, it looks like I am opening something called employee health data. Double-click the name of that file, and the data file opens in the Jamovi spreadsheet. You're now ready to perform the analyses. I'm on page 7, top of page 7 of my lecture. Requesting descriptive statistics in students' t-test. Our analysis will address the following research question. Students who are employed while enrolled in college will report lower levels of overall health compared to students who are not employed. In this analysis, the criterion variable is going to be health. It was assessed using multiple item summated rating scale consisting of items such as, in general, my health is good. Scores on the scale can range from 1 to 7. Higher values represent better self-reported health. This was a quantitative variable, and we can view it as being theoretically continuous. The predictor variable in our analysis is employment. This is a subject variable consisting of 2 conditions. Subjects who were working at a paying job at the time they completed the questionnaire constituted our employed condition. Those who were not working at a job constituted the not employed condition. First up, we will request plots and descriptive statistics. To begin this process, click the Analyses tab to reveal the Analyses ribbon at the top of the Jamovi interface as shown in the following figure. From this ribbon, select the Exploration icon, and from the resulting menu, select Descriptives. I illustrate this in the next figure. At the top of the Jamovi interface is the number of tabs. Make sure that the tab labeled Analyses is selected. Then go to the Exploration icon and click this Exploration icon. It will produce a menu. From that resulting menu, select Descriptives. Doing this will produce the initial Analysis Options panel for the Descriptives procedure as shown below. Below the heading Descriptives is the variable list box, the box that displays the names of all the variables in the data set. So I'm still on page 8. On page 8, this is what the Analysis Options panel for the Descriptives procedure is. You know it's the Descriptives procedure because it says so here. Names of all of our variables initially appear in this variable list. From the variable list box located directly below the heading Descriptives, select Health and click the right pointing arrow to move it to the box labeled Variables. From the same variable list, select Employment and click the right pointing arrow to move it into the box labeled Split By. That's a different box. In a second, we'll see. If necessary, click the small arrow icon next to the heading Statistics to reveal the names of the various procedures that can be requested. Then check the necessary boxes so that your panel resembles the following figure. If necessary, also click the small arrow next to the heading Plots and reveal the different kinds of graphs that can be requested. Check the boxes to identify that are identified in the following figure. So I illustrate this in my screen capture of the Jamovi interface here on page 9. Yeah, on page 9. Variable health had been over here in the variable list. I selected it, clicked this right pointing arrow and moved it into the big box headed variables. Employment had been over in this big box. I clicked it and clicked the right pointing arrow to move it into the box headed Split By. If the statistics options were not visible, I clicked the little arrow to the left of statistics to reveal all those options, and then I checked the boxes so that it looked like this. By the same token, if the section headed plots was not visible, I clicked the little arrow to the left of that heading, and from the resulting options, I checked and unchecked boxes so that these options had been selected. Adding your name to the results panel. Some exercises in this course will direct you to add your name to the Jamovi results panel. Here are the steps for doing this. It is not complicated. As soon as you put some variables into those boxes in the previous figure to request the analyses, your results would appear in the results panel. Click the heading results, and on the line directly below it, type something like analysis by and provide your name. In this case, you can see I indicated analysis by Larry Hatcher. I am still on page 10, bottom half of page 10. Checking assumptions and screening data. Are you sure that your data satisfy the assumptions required by the independent samples t-test? We shall find out. Scroll down to, where am I? This is page 11, and we have this section. Table of descriptive statistics. Following figure presents part of that output. The table of statistics created by the descriptives procedure. The table itself appears on page 12. And before we look at the details, let's get oriented. Leftmost column in this descriptives table is headed descriptives, and below it we have the names of the statistics being reported. So means are reported to the right of this heading, median to the right of this heading, so forth. We have a heading employment, and below that we will see which groups are being compared. Remember, employment was the dichotomous variable that coded whether somebody was not employed versus employed. So to the right of not employed, we see statistics for the non-employed people. To the right of employed, we see statistics to the for the employed people. The name of the criterion variable appears here, and in this case, it is health. Remember, this is self-ratings of physical health. So all those statistics for the health variable are in this column. What do we have? The two samples are relatively large and very similar in size. What does he mean by that? Well, we're looking at the statistics in, that is sample size, the number of people in each subgroup. And it looks like we've got 114 people who identified as being not employed, 124 as being employed. Those are fairly big numbers and fairly similar to each other. That is good news. Variances are similar in the two samples. What do you mean by that? We're looking at variances. The variance for the employed people is 0.83. Variance for the for the not employed people is 0.83. For the employed people, it's 0.91. Those variances are similar to each other. In a minute, we'll see why that is a good thing. Scroll down. I am on the bottom of page 13 now. Bottom of page 13. Frequency histograms. In the plot section of the descriptives analysis panel, you requested several different types of graphs. Following figure presents frequency histograms. For both groups, long tail extends in the direction of lower scores, indicating that both distributions were negatively skewed. There's frequency histogram for the not employed people. Now, the variable we're looking at are self-ratings of health. Most people rated themselves as being relatively healthy, but there was a small number of people who rated themselves as not being healthy. They were few and far between. They created a long tail in the direction of lower scores, and that means this is a negatively skewed distribution. We see pretty much the same shape when we look at the people who were employed. Negatively skewed distribution for both samples. Box plots tell the same story. Same negative skew can be seen in the box plots presented below. Here's a box plot of health scores for the not employed people. We have a longer whisker in the direction of lower scores for the not employed people. And we see the same long lower whisker for the employed people. That's consistent with the idea that we've got a negative skew. People in my department are very interested in using QQ plots as a way of determining whether you have normally distributed data or not. So on page 14, bottom half of page 14, we're looking at QQ plots. They can be useful in assessing normality assumption. Following figure presents QQ plots for the current data. Now, a lot of folks look at this and wonder, well, what does that mean? I don't even know how to interpret that. If the scores in the sample are normally distributed, data points in a QQ plot should fall directly on the straight diagonal line that extends from the lower left to the upper right corner. Unfortunately, the data points in this figure do not do this. They instead take the form of a curved line, which once again is the signature of the skewed distribution. If our sample was perfectly normal, all of these dots would fall exactly on the straight line. The fact that they don't fall directly on the straight line means we don't have a perfectly normal distribution. We see the same story when we look at these employed people. Well, conclusions regarding assumptions. We've got skewed distributions, but is it so bad we can't do a t-test? One of the assumptions underlying the t-test is normally distributed data. On the negative side, our analyses show that both the employed and not employed groups displayed negatively skewed distributions with a few outliers on the lower end. On the positive side, however, number of participants in the not employed group, 114, is very similar to the number of people in the employed group, 124, and the combined sample of 238 easily exceeds the recommended size of 30 or 40. Lucky for us, students T is known to be robust against violations of the normality assumption under such conditions. Robust means strong. Robust means it'll give us the correct results even if there are some violations of the assumption. What about homogeneity of variance? This is the requirement that scores in the two conditions must come from populations with equal variances. Some suggest that when you're doing an independent samples t-test, this assumption is satisfied as long as the variance for one group is no more than twice as large as the variance for the other group. For the current analysis, previous figures showed that the variance for the not employed people was 0.83, while the corresponding value for the employed people was only slightly larger at 0.91, indicating that this homogeneity criterion was satisfied. If this variance had been twice as big as that variance, then we would have cause for worry. In this case, we do not. We don't need to worry much about that homogeneity of variance assumption. So let's go ahead and do our t-test. Requesting the independent samples t-test. I'm on the bottom of page 15 now. To request the t-test, you click the Analyses tab if necessary to reveal the Jamovi Analyses ribbon. From this ribbon, click the t-test icon. From the resulting menu, select Independent Samples t-test as shown in the following figure. On page 16, top of page 16, it goes like this. If necessary, click Analyses tab so that you see the Analyses ribbon. From the resulting Analyses ribbon, click T-Test. This produces a menu. From the resulting menu, select Independent Samples T-Test, and that should produce the Analysis Options panel for doing a T-Test. In fact, that's what my text says. This opens Independent Samples T-Test procedure in the Analysis Options panel, as shown in the following figure. This is the Analysis Options panel for Independent Samples t-test. Once again, variable list is on the left. These are all the variables we could analyze. Identifying the variables that we will analyze. I'm on page 17 now, top of page 17. Identifying variables to be analyzed. Select health from the variable list and click the right pointing arrow to move it into the box labeled dependent variables. What do you mean by that? Health had been in this large variable list. Select it, click the right pointing arrow, and put it in the box headed dependent variables. Select employment from the variable list and click the right pointing arrow to put it into the box labeled grouping variable. Employment had been over here. I selected it and I clicked this right pointing arrow to move it into the box headed grouping variable. Requesting options for the t-test. There's a long list of tests and statistics that we'll need for the research report. So in the Analysis Options panel, check the various options until your panel looks like the one illustrated here. So make sure that you check and uncheck boxes so that your Analysis Options panel for Independent Samples t-test resembles this one. We scroll on. I'm on page 18 now. Toward the top of page 18. Interpreting results from the analysis. General trend of the results. Our first step is going to be to review the two sample means. They appear in the jamovi results panel in a table headed Group Descriptives and are reproduced below. Now remember what this analysis is all about. We are hoping to find that the employed people will report a lower level of physical health compared to the not employed people. Here we have Group Descriptives table. Mean score for the not employed people is 5.60. Mean score for the employed people is 5.33. Remember, higher scores indicate better health. So we are pleased to see that the mean for the non-employed people is in fact higher than the mean for the employed people. Now, at this point, we don't know if it's a big enough difference to be statistically significant and substantial, but we will find out. Output shows that the mean for the non-employed students was 5.60. The mean for the employed students was lower at 5.33. These values and their 95% confidence intervals are illustrated graphically in figure 530.20. That is the figure on the next page at the top of page 19. We have this figure that illustrates the same means and their 95% confidence intervals. Our research hypothesis predicted that the non-employed students would score higher than the employed students on self-reported health. So far, the trend displayed by our obtained sample means is consistent with this hypothesis. Again, at this point, we don't know if it's a big enough difference to be statistically significant and meaningful. I'm now on page 19, toward the top of page 19. Null hypothesis significance test, students t-test. This is where we'll find out whether we can reject the null hypothesis. Go to page 20, about halfway down page 20. Well, what null hypothesis is being tested anyway? If being employed has no effect on health at all, then the mean health score reported by the employed students should be exactly equal to the mean health score reported by the not employed students. This, in fact, is the statistical null hypothesis that we'll test in the current analysis. Here's one way of stating it. In the population, the mean health score for the employed students is equal to the mean health score for the not employed students, where mu sub 1 represents the mean health score displayed by the population of not employed students. Mu sub 2 represents the mean health score displayed by the population of employed students. Notice that preceding used the Greek letter mu as a symbol for mean score in the population. If being employed has no effect on health at all, then mu sub 1 should be exactly equal to mu sub 2. There is a second and equivalent way of stating the same statistical null hypothesis, and it's actually the second approach that will be emphasized in this chapter. Here's an equivalent way of stating the same null hypothesis. Mu sub 1 minus mu sub 2 is equal to 0. In the population, the difference between the mean health score for the employed students versus the mean health score for the non-employed students is equal to 0. The second approach above acknowledges the fact that if the two population means are equal, then subtracting one population mean from the other should result in a mean difference of 0. The obtained t-statistic and its p-value. To determine whether we can reject this null hypothesis, we review the obtained t-statistic. We scroll down. I'm on page 21 now. Toward the top of page 21. In figure 530.21, the obtained t-statistic for the current analysis appears below the heading statistic. There, we can see that the value is 2.16. Well, that's our obtained t-statistic. In figure 530.21, below the heading P, we can see that the obtained probability value for this t-test was 0.032. In an earlier chapter, we learned that the obtained probability value represents probability of obtaining a statistic as extreme as the current statistic if the null hypothesis were true. The current p-value indicates that if the null hypothesis were true, probability of obtaining a t-statistic as extreme as 2.16 is just 0.032. This is a fairly small probability. But is it small enough to reject the null hypothesis? Wait a minute, where do all these statistics come from? You say the t-statistic is 2.16. Where did you get that exactly? That would be in this output down at the bottom of that page. At the bottom of page 21, this output is the results produced by Jamovi when we requested the independent samples t-test. Below the heading 1, we have this heading statistic. This is our obtained t-statistic. This is the t-statistic of 2.16 that I alluded to. What about this p-value? We have to call out number 2 and the heading P. Below this, we find the obtained probability value associated with the t-statistic. My obtained probability value is 0.032. Now, if being employed has no effect on health at all, then our t-statistic should have been 0, and this p-value should have been like 0.99, but that's not what we found. Our obtained t-statistic was 2.16. That's pretty far away from 0, and its associated p-value is 0.032. This p-value tells us if the null hypothesis were true, if there's no difference at all between employed and not employed people in the population, the probability that I would have gotten a t-statistic as extreme as this one, as extreme as 2.16, that probability is just 0.032. That is a relatively small probability. Probability of just 3%. But is it small enough for us to reject the null hypothesis? Let's go up to where we left off. I'm still on page 21. Current p-value indicates if the null hypothesis were true, probability of obtaining t-statistic of 2.16 is just 0.032. It's a small probability, but is it small enough to reject the null? To decide, we'll compare this obtained p-value to the alpha criterion. This is our Greek letter alpha. To the alpha criterion we had selected prior to analyzing the data. Earlier, we saw the alpha criterion represents the size of the region of rejection in a theoretical sampling distribution of the test statistic. Researchers typically set the alpha criterion at either 0.05, 0.01, or 0.001. Let's assume that we went the most popular choice. We set alpha at 0.05. In the current analysis, our obtained probability value of 0.032 is smaller than the alpha level of 0.05. And yes, 0.032 is smaller than 0.05. This means we can reject the null hypothesis. We can tell the world there is a statistically significant difference between the mean health scores displayed by employed versus not employed students. So that's one piece of the puzzle. We know we can reject the null hypothesis. We can tell the world we've got significant results. But there's more. What about the confidence interval? I am still on page 21. The mean difference and its confidence interval. In the figure below, the column headed mean difference, we can see that the size of the difference between the two means is 0.26. Is that true? Below this callout number 3, we have this heading mean difference, 0.26. What does that represent? Oh, that's the difference between the mean health score displayed by the not employed people versus the employed people. It was a difference of 0.26. This value was computed by subtracting the mean health score for the employed students from the mean health score for the not employed students. Now, this mean difference of 0.26 is a point estimate. It's a single value that serves as our best estimate of the size of the difference between the two groups in the population. Point estimates almost always involve some degree of error, so it's good practice to supplement them with confidence intervals whenever possible. A confidence interval, I'm on page 22 now, a confidence interval is a range of plausible values for the population parameter being estimated. An interval that helps readers decide how much faith they should have in the precision of that estimate. Figure 530.21 reports that the 95% confidence interval for the current mean difference extends from a lower limit of 0.02 to an upper limit of 0.50. Now, where did that come from? Well, the callout number is 0.4. Here it is. The mean difference was 0.26, and its 95% confidence interval extended from 0.02 to 0.50. That is where that confidence interval was found. When viewed together, this point estimate that we mentioned before, along with its confidence interval, suggests the following. Our best guess is that the population of not-employed students scored about 0.26 points higher than the population of employed students on our 7-point measure of physical health. However, it's plausible that the actual difference might be as small as 0.02 points, or it might be as large as 0.50 points. That is what we learned from our point estimate and confidence interval for the mean difference. I am still on page 22. We come to a new and very important statistic, an index of effect size. Earlier, we learned that the t-test for the current investigation was statistically significant, although this allows us to reject the idea that the difference between the two population means is equal to 0. The t-statistic by itself doesn't tell us anything about the relative magnitude of the difference. Does it represent a powerful effect, trivial effect, something in between? To make this determination, we must consult an entirely different type of result. We must consult an index of effect size. Index of effect size is a statistic that represents the magnitude of the difference between two means, the strength of the association between two variables, or some similar concept. This chapter is going to focus on the most popular choice for this kind of research design. Cohen's d statistic will be our index of effect size. Cohen's d statistic reflects the size of the difference between two means as measured in standard deviations. And I provide the formula, the generic formula for Cohen's d there. Let's keep scrolling. I'm on page 23 now. We requested that jamovi compute Cohen's d statistic when we checked the box labeled effect size in the analysis options panel for the independent samples t-test shown earlier. Resulting statistic was then reported in the output shown below, below the heading effect size. Now pause. Where's this? Call out number is 5. Okay, there it is, effect size. Our effect size for this analysis was 0.28. That means Cohen's d statistic for this analysis was 0.28. There we can see the computed value is d is equal to 0.28. This indicates that the not employed students scored 0.28 standard deviations higher than the employed students. That's our effect size. Well, what does that mean? Is it a big effect, small effect, or what? To interpret these statistics, Cohen recommended comparing them to the typical index of effect size obtained in other studies that dealt with the same or similar constructs. When this was not possible, he suggested the following criteria, which we will refer to as Cohen's last resort benchmarks. If it is bigger than 0.20 in absolute value, we'll call it a small effect. If it's bigger than 0.50, we'll call it a medium effect. And if it's bigger than 0.80, we'll call it a large effect. This researcher, Sawilowski, thought that Cohen didn't give us enough criteria. He kind of stopped at a large effect, and he thought he should give us more gradations of effect size. So Sawilowski provides his suggestions for how to interpret an index of effect size. They are similar to Cohen's, except he goes into the bigger effects that are possible and also the smaller effects that are possible. Let's continue to page 24. Regardless of which of those systems we use, the d statistic obtained in this analysis, 0.28, is larger than the criterion of 0.20, which represents a small effect, but is not larger than the criterion of 0.50, which represents a medium effect. Therefore, we'll interpret our current value of 0.28 as representing a small effect. Confidence interval for the effect index. Remember, this d statistic, 0.28, is just a point estimate of the actual effect in the population. To provide readers with some sense of the precision of this estimate, we'll also report a confidence interval for it. The results were then provided in the columns headed 95% confidence interval to the right of the heading effect size in the figure. The call-out number is 6. Now hold on before we go any further. What is he talking about? There's the call-out number 6, 95% confidence interval. oh, this must be the 95% confidence interval for the index of effect size, 95% confidence interval for Cohen's d. It extends from 0.02 to 0.54. Is this what the text says on page 24? Results were then provided in the column 95% confidence interval to the right of effect size. These columns show that this confidence interval extends from the lower bound of 0.02 to the upper bound of 0.54. By putting them together, we can say the following. Our best guess is the Cohen's d statistic is equal to 0.28 in the population, but it's plausible it might be as small as 0.02, might be as big as 0.54. Now, my chapter on this topic continues, but Hatcher stops lecturing here. This is the end of the material that's relevant to the jamovi exercise 050-01 t-test for independent samples and the corresponding multiple choice quiz. So you now know the things that you need to know to be able to complete the exercise in this unit. Now remember, I don't expect you to do the analyses that I just demonstrated with my data set. You'll perform these analyses, but you'll perform them on a different data set. You will use a different data set and compute the t-test for independent samples.